Hi, my name is Mohammed, and today I will be showing you how to use the program Strata. So Strata is one of available softwares in practice that can be used to perform one-dimensional site response analysis, and you'll be using it in your project to perform 1D equivalent linear analysis in the frequency domain, but using input time series. So if you remember from the first demonstration, we talked about selecting a suite of 7 ground motions that fit on average your target response spectrum. So that is the first step. You have to get your input motions. And then you also need the subsurface model, your soil properties, the layers, the shear velocity, and the dynamic soil properties, G over Gmax and damping. And once you have the input motions and your subsurface model, you will use Strata to perform computations, particularly to propagate these 7 motions from the bedrock through the soil to get the predicted motion at the surface. So that's how we'll be using Strata to perform the equivalent linear analyses. Before we get started, you have to download Strata, and we will provide you with a document that includes instructions on how to do that. You will simply go to this link, which will take you to a GitHub page, and you have several files which you can download. And in the document, I discuss which file you have to download based on your operating system. Once you download it, you can go through the installation steps, and it should be straightforward. So once you have Strata downloaded and installed on your desktop, you can navigate to where it was installed, and you should be able to see these files and folders. And it's very similar to Sigma Spectra. Actually, the same person who developed Sigma Spectra also developed Strata and is still maintaining both of these. So if you go to the doc folder, that's where the manual is. The manual mainly focuses on providing theoretical background for site response with equations, etc. But they do have two examples. One of them is time series, which is similar to what you'll be doing for your project, and the other one is not really relevant. So if you want to look at an example, you can look at the time series example in the manual. To actually open Strata, you will double click on this icon over here, and that will open Strata's window. And actually, I believe you can search for Strata and it will appear and you can open the application. So that is Strata's window. So there are a lot of software out there in practice, but we'll be using Strata for the project simply because it will walk you nicely through the steps that are required. And that is done through these tabs: general settings, soil types, soil profiles, motion, output specification, and compute. So it should be straightforward to use for your project. Before we dig into Strata, let me just show you the site we'll be using for today's demonstration. So today we'll be looking at a site from Anchorage, Alaska, and we'll be performing 1D start response for the site. Actually, for my dissertation, I'm looking at 2 sites. One of them is the Treasure Island that you are working on for your project, and the other one is this site in Anchorage, Alaska. And here is just an overview of the model at the site. This is a simplified shear wave velocity. We have 3 layers. The top layer is what we call a glacial outwash. The second layer is a thick clay layer of around 35 meters. And below that is a glacial till, which has a shear wave velocity of around 1,000 meters per second. And we will assume that to be our bedrock. So let's go into Strata. The first thing is it's always good to give your demonstration, your project a name, a title. So I'll just call it demo, and make sure the units are metric. You can select English units, but we'll be using metric units for the project. And then on the right, you have to specify a number of options. The first one is the type of analysis. You have the method. It can either be linear elastic, equivalent linear, or frequency dependent equivalent linear. You don't have to worry about that. Simply for your project, select equivalent linear. And then you have the approach. You have either time series or random vibration theory. Remember, we developed 7 acceleration time series, and thus for your project, you'll be using the time series approach. So simply select time series. One thing you can do within Strata is you can vary the properties. Remember, shear wave velocity and also our properties, we have uncertainty. There is uncertainty, there is variability. And one way to account for that is by varying the properties using a Monte Carlo approach. And you can do that within Strata by checking this box and selecting few input parameters. But for your project, that's an advanced option. I guess you'll not be accounting for uncertainty in this way. I believe for your project, You will be accounting for uncertainty by simply taking the base case UV velocity profile and multiplying it by plus minus 10 to 20%. So uncheck this box for your project. One thing you will actually be interested in is this calculation parameters tab. So first we have the error tolerance, and in this case, the default value is 2%. If you remember, the equivalent linear approach is based on iterations. We are iteratively updating our G over G max and damping to be compatible with the induced strain. And thus, we eventually have to stop at some point, and that is specified by these calculation parameters. The first option is to specify an error tolerance, and that is the error between two successive iterations in the soil properties, meaning Strata will stop calculations for emotion once the difference or the error between two successive iterations in terms of the soil properties, G over G max and damping, is 2%. That's when the iterations will stop. Another option is to specify the maximum number of iterations. In this case, it's 10. So if, let's say, at iteration 10, the error was still greater than 2%, in this case, it will stop simply because you've specified a maximum number of iterations of 10. So actually, you'll be able to see the error later on in the compute tab, and it's always good to check the error and make sure the results are converging to an error tolerance below 2%. Otherwise, you can come back to here and change the maximum number of iterations. Another option to specify is the effective strain ratio. Let me go back to my presentation to simply talk about the effective strain ratio. So as I said, the equivalent linear approach requires your nonlinear soil properties to be compatible with the induced strain. And here, gamma, that's the strain, not unit weight. And because you have an acceleration time series in which the acceleration changes with time, your strain will also change with time. And here in blue, we're just seeing a strain time series for this top layer. And we eventually have to assign a single strain value for each layer. So what should we use? One option is to use the maximum strain value, but really that occurs only at one single point in time. So is it appropriate to use that as our design? Probably not. So actually in practice, we use an effective strain level, and usually we simply multiply the maximum strain by a fraction less than one, and typically 0.65 is used in practice, and that is the number that's specified over here, 0.65. And you will talk more about that in class. So simply, we are updating our G over G max and damping such that to be compatible with a strain of 65% of the maximum strain induced in our layer, in each layer. So one other important thing is the layer discretization, and let's talk about that also. So again, we are updating the properties within each layer to be compatible with the induced strain. But if you think about it, the strain will vary with depth, even within the same layer. If you look, for example, at this thick layer, it's impossible that this thick layer, all of it will have a single strain value. So how can we account for that? We have to assign the multiple values of strain for that layer. And we do that by simply discretizing our layers into thinner layers. And these are the ones shown in gray over here. So we simply divide our layers into thinner layers so that we have a smoother strain profile that more realistically matches the actual change in strain with depth. Otherwise, if we only use one thick layer, it will have only a single strain value, which is really not realistic. So that's why we discretize our layers. And to do that, you have two parameters, and that will determine how thick your discretized layers are. And these parameters are the maximum frequency and the wavelength fraction. Usually we use a wavelength fraction of 1 over 5.2, and the maximum frequency can be anywhere between 20 to 25 hertz. And we'll also discuss that in class. And the nice thing about Strata is you don't have to do the discretization yourself, meaning you don't have to divide these sublayers yourself. Strata will do it for you. And note that not all programs will do that. So that's one nice thing about Strata. It does the auto discretization for you. So that's a nice thing within Strata. You can disable it if you want to, but then you will have to input in the soil type and the soil profile, the discretized soil profile. So with that, we have defined everything we need from the general settings tab. So now we can go into the next tab, which is soil types. So in Strata, you define your soil types, which includes like the unit weight, G over G max damping, separate than the soil profile. So in the soil types, you define this unit weight, G over G max damping, and in the soil profile, you assign the thickness of each layer and its shear velocity. So we will start with the soil type. So it's simply, before we start with the soil, let's look at the bottom. We have our bedrock layer. So for the bedrock, you will input a unit weight, and let's use a value of 20 for our case, and you will input a damping, and we'll use 0.5. Usually for the half space, you will still model it as linear elastic, and you simply need the unit weight and the damping as input. Another thing you have to specify is the water table. And we will use, I guess for our site, it was around 20 meters. Yes, so these are the dynamic properties at the site. For the glacial till, which we are assuming as bedrock, we have a unit weight of 20 kilonewtons per meter cubed, and we will assign a damping of 0.5. And then we have our groundwater table at a depth of 20 meters. So we'll go back over here, put a water depth at 20 meters. Note that the water depth is not very critical, and we are still performing total stress analysis. We are not using effective stress analysis. And the water depth is simply used to compute some outputs in terms of effective strains. So it's not really a critical parameter, but make sure to have the correct value over here. So to now we have to start adding our soil layers. So we have two soil layers. So we go over here, we click add. The first thing is you have to give it a name, and you can name your layers whatever you want. So I'm going to name the first one as outwash and the second one as clay. So outwash, then the second layer, I'm going to name it clay. Then you have to assign a unit weight for each layer. So I'm going to use 17 and 17.5. Let me just check, 17, 17.5. Then we have to assign our G over G max and damping models. And Strata has already some predefined models. So if you double click over here, you can down click on this arrow and you have several options. Let me just increase this. So now we can look. So if you click custom, you will simply create separately a G over G max, and then you come over here to this white space and you right click and paste. So like you can copy from an Excel sheet, etc. First column should be strain in percentage, the second column should be G over G max, and you paste it over here. Otherwise, you can calculate things within Strata. So you can specify a certain model. For example, it has EPRI with a plasticity index of 10. So if you click on this, and now you look, we have a predefined G over G max curve with strain in the first column and G over G max in the second column. You can select Derndelli and Stokey. And if you select that, just give it a minute, you should be able to update these values over here. So you see now, since we've selected Derndelli and Stokey, you have to give it some input parameters. Derndelli and Stokey is a function of several input parameters, including the mean effective stress, the plasticity index, the overconsolidation ratio, excitation frequency, and number of cycles. I will get back to this in a minute, but let's first of all select Derndelli and Stokey for all of our soil layers. But again, you have several options which you can go through and select the one you believe is the most appropriate for your soil. So I'm going to select Derndelli and Stokey for both G over G max and damping. And then we will assign the properties for each layer. So let me just go back. The first layer we're modeling it as sand, not as clay, with a plasticity index of 0, mean effective stress of 0.67 atmosphere. So we'll go back to Strata, and over here, we will select a mean effective stress of 0.67. Remember, everything for the mean effective stress is in units of atmosphere, so make sure you make the correct conversions. We'll leave a plasticity index of 0 and an OCR of 1. But then you have this frequency and number of cycles. I'm not sure if you've talked about these in class, but people have found that the G over G max and the damping will change with frequency and the number of cycles that they used in their laboratory tests. But typically for earthquakes, 1 hertz for the frequency and 10 cycles are good numbers. So use 1 hertz and 10 for the number of cycles. So you only have to input the mean effective stress, the plasticity index, and the OCR. And I'm going to go to my next layer. This has a plasticity index of 35. This is a clay layer, an OCR of 1.5, and mean effective stress of 2.7 atmosphere. So I'll go back to Strata, And for the G over G max, I'm gonna input the mean effective stress of 2.7. So you have to do these calculations for the mean effective stress yourself in an Excel sheet, etc. You calculate the mean effective stress at the center of each layer, convert it to atmosphere, go over here and put the right values. Then plasticity index of 35, we're gonna OCR of 1.5. And you see like every time I change a value, the G over G max curve will change. Look, let's go back to 30, to 0. You see how the values are changing. 35. It updates automatically, so it will calculate the correct G over G max for you based on the Rindalia and Stokia and based on the input parameters that you are defining over here. So we've defined these, and it should up if you select Darendalia and Stokie for both the G over G max and the damping model, it will update them based on the parameters you defined. So remember we had 0.67 atmosphere for this layer and the G over G max, so it updated it automatically for the damping model, but it's always a good idea to check and make sure everything is correct. And for this one, it should be 2.7 atmosphere. We have 2.7 plus this index of 35, 1.5 OCR, 1 and 10. So everything looks good. And then you have this damping limit option. So this column, let's say in your analysis, you had a damping of 5%. Let's say you set over here a damping of 5%. So what will happen in the analysis, it will enforce this as the minimum damping level. No matter what the actual strain compatible damping is, it will force it to have a minimum value of 5. So for your project, simply select a very low number so that you're not affecting the damping value. And this, if you select a low number, the damping will still be compatible with the induced strain. You're not changing anything in the analysis. You can add nodes if you want to, but for now, don't add any nodes. So everything is good. You can also put damping limits of 0 if you want to, but 0.5 is good. So we have defined so far the soil types for these two layers. One thing to note is sometimes you would like to break your layers further. For example, this layer over here is 35 meters thick, and we are assigning it a single mean effective stress based on the middle value only. And that will control the G over G max and the damping curves, because remember the G over G max and damping curves are a function of the mean effective stress, which actually changes with depth, but we are assigning a single value for the entire layer. So ultimately, you might want to break your layers into like smaller layers. For example, maybe break this clay layer into 2 or 3 layers so that you have a different mean effective stress, and thus you have better G over G max and damping curves. Remember, this is different than the sub-discretization we talked about earlier. So this is simply for the equivalent linear computations, but for the iterations. But here, we are assigning to begin with initially a G over G max and a damping curve for each layer. And that is a function of the mean effective stress. So this entire layer will have the same G over G max and damping curve. And even if we go back to these discretized layer, all these small layers within the same layer will have the same G over G max and damping curve, but each layer will have a different strain value, and it will have a different G over G max value based on the strain value, but from the same curve for each small layer within the same big layer. But we know that the G over G max and damping curves change as a function of the mean effective stress. So if you have a thick layer, it is recommended that you divide it into like 2 or 3 layers such that you have a different mean effective stress for each layer and thus more representative G over G max to assign for your analyses. But in this case, for simplicity, I will keep it as one layer. And I believe for your project, you already have your profile in small layers, so maybe you don't have to do that, but it's something to keep in mind. So now we have defined our soil types. So we can go to the next step, which is the soil profile. Before I move to the soil profile, make sure you input the bedrock layer properties, which are at the bottom. So now we go to the soil profile. You have by default the bedrock, and anything that's in gray, it is something you cannot edit. You can only edit white cells. So our bedrock has the shear wave velocity of 950 meters per second. So we will input that, and then we will start adding layers. So we will add layer, add layer. I'm gonna add one more just to show you how to remove a layer if you added one accidentally. So we're going to start from the first layer, and you will input the thickness for each layer. My first layer has a thickness of 12 meters. So I will go over here and put 12 meter. And then the second layer, you see how everything updated, like how the depth updated and these gray cells, which you cannot change, gets updated on their own. Then the second layer has a thickness of 34 meters. So I'll go over here, I'll put 34, and that will update everything to 30 to 46. So see now we have 46, 46. But let's say you added the layer accidentally by mistake. So what you do is you simply click over here. That will select the entire column and you can click remove. Let's say you want to add a layer between these two. You click over here and you click insert. So that will add a layer between them. But I don't want that layer, so I will click remove. So I've defined the thickness for the first layer, the thickness for the second layer, and that automatically updated the depth to the bottom to the top of each layer. So now my half space is at 46 meters. Let me double check. Yes, my half space is at 46 meters. So that is good. So now we've defined the thickness. Let me update the shear velocity for each layer. The first layer has a shear velocity of 300 meters per second. 300 meters per second, and the second layer 250 meters per second. So I'll go over here, 300 to 250 meters per second. But then we have to assign for each soil layer its G over G max and damping curve from the previous tab. So here we defined soil, the G over G max and the damping model. So we have to link each layer to which G over G max and damping model we want to assign to. And that is simply based on the name that you defined over here. So that's why these names are important. So if you go to soil profile under soil type, if you click over here, you can select what you defined in the soil type. So this layer, I know it's the outpush layer, so I will select outpush. That will assign the G over G max and damping curves that you defined over here for this first layer. You can assign multiple soil types for several layers. Like I can also click over here and assign outwash to this, but that's not correct. The second layer is clay. So make sure to link each layer in your soil profile to its appropriate soil type, which includes the G over G max and the damping values. So now we have defined our soil profile. We have our subsurface model with everything. If you go back to the slides, we have our layer thicknesses, we have our shear velocity, we have our G over G max, we have our damping, we have our unit weights. Everything has been assigned to each layer. So we have our subsurface model. So now we have to select the input suite, the suite of motions. So let me go back over here. That is the next tab, motions. So the first thing is to select where these motions will be inputted, where we will input the motions. And you can click over here, you can either specify a depth or select Bedrock. So if you select Bedrock, Strata already knows that Bedrock is at 46 meters, so it will input these motions at the level of Bedrock, which is what you have to do for your projects. Remember, we have selected input motions that are representative of rock-like conditions, and we will input these motions at the level of rock, propagate them through our soil profile to get the predicted response at the surface. So we will select for your project, the location of the input motions is rock. And then you come over here and you have to add your input motions. You can add them one by one manually, or you can select load suites. I will just show you how to add one by one manually. So you click on add, and you have to navigate to where your input motions are. So let me go back. So let's say I selected this motion. And click OK. Point count time step 0.5. So it's not a response. Just give it a second. So here my motion got loaded. You can see it will give you the name of the motion. It will give you its type, it's give you its PGA, it's give you its PGV and scale factor. So it automatically loaded these options. But if you add a motion, so the motion I selected right now, it's not from the peer database. So that's why it didn't read it automatically. But if you select a motion from the peer database, which is what you're using for your project, it will automatically read it and input these options. So let me select this one over here. So that's from the peer database. So you see how it selected all these input inputs automatically, you simply click OK, and it will add this motion. So that's one way to add your motions manually. And if you do that, you have to select the scale factors that you used to match the target design response spectrum over here. So you have to add these manually, whether the scale factor, let's say was 0.5 for this motion, etc. But if you have done your scaling within Sigma Spectra, you can simply load the entire suite of 7 motions that fit your design response spectrum without having to add them one by one manually. So I will simply remove these. You click over here, it selects the entire column, remove, click over here, remove. Then I will go to load suites. So remember in yesterday's demonstration, I showed you how to save a suite in both CSV and Strata format. So if you saved it in Strata format, you can simply load this suite. So that's the suite that I saved. So I will click on it. It's called Suite 1. That's the same suite I showed you in the demonstration. Click Open, and it should load everything automatically without having to input each motion individually. So you see, now we have 7 motions. We had 7 motions in our suite. It will give you the description of each one. It will give you the type. So in the type, you have 2 options, either outcrop, if you double click over here, or you can select within, and we'll talk about that in a minute. You see, you have within, you have incoming, etc. For your project, you will be using outcrop, meaning all of these motions were recorded on outcropping sites at the surface. So we'll select outcrop. That's the correct one. You cannot edit PGA, you cannot edit PGV because it's simply reading those from the input file. And you see it automatically loaded the scale factors from Strata, Sigma Spectra. So you don't have to change these yourselves. But it's a good idea to make sure the values were imported correctly into Strata. So make sure to save your suite in Strata format so you can easily load it into Strata and you don't have to input each one individually. So now I have my suite of 7 motions. Finally is the compute tab. So sorry, I have the output specification before that. So we finished general settings, role types, solid profile motions, and now we have output specification. I hope by now like you can see how all these pieces you've been learning in the class are coming together. We have learned how to select a suite of motions, and we had to input the motions over here. We have learned about G over G max, damping, soil properties, etc. And like all these pieces will come together to perform your 1D site response analyses for your project. So Strata will give you a lot of output, and you may or may not want to look at all of these. So you have the option of selecting what output you want to see instead of looking at everything. So within the output specification, you have several tabs. You have profiles, time series, etc., etc. So profiles is simply looking at things as a function of depth, as a function of the subsurface depth. So you can select, for example, the initial shear wave velocity profile. So that is the VS profile that we input in the soil profile tab. So you can look at that. But you can also look at the final shear wave velocity profile. Remember, within the equivalent linear approach, we are updating G over Gmax and damping to be compatible with the strain. So if G over Gmax is changing, then your VS is changing. So what Strata will do is, once it has the updated G over Gmax that is compatible with the strain, it will back calculate the actual shear wave velocity and it will plot that as the final shear wave velocity profile. So you can also look at that. You can look at the peak ground acceleration with depth. You can look at, for example, let's see, the maximum shear strain profile. You always, always, always have to look at the maximum shear strain profile. It is always a good idea to see how much strain is being induced within your profile. So always look at the maximum shear strain profile. You can look at the peak ground velocity. You can look at several options, but that is enough. So remember, we had the groundwater table input, and I told you it's not as significant. It won't really affect much the results, but it is only used, for example, for the vertical effective stress profile, but it does not affect your analysis. You are still doing the analysis within a total stress framework. So I've selected what I would like to see from the profiles, things as a function of depth. The second tab is the time series. So here you will get specific output in terms of like time series at a specific depth. If you want to select a time series, you click add, and it will give you several options. Like, do you want to see the acceleration time series, the displacement? Usually you will not look at time series, so I will not go over that. I'm just going to click cancel. More importantly is looking at response and Fourier spectra, and that is the third tab. So here you can select to see the response or Fourier spectra at a specific depth. So you can click add and it will give you two options. It can give you, you can select either the acceleration response spectrum. So I'm going to click that, click OK. It will show up. You will have to tell it at what location you want to see this response spectrum. You can select the 0 meter, or like that's the surface. You can select bedrock, or if you want like a specific depth, you can specify a depth. I'm going to click 5 meters, whatever you'd like to see. Usually you'd look at the surface and the bedrock. So I'm just going to look at the surface, which has 0 depth. And you have to specify the type. The key in this project is always going to be outcrop. We're going to be always using outcrop. We usually use other types such as within, etc., for research purposes. And in your project, everything is recorded on the surface. The 0 meter, that's the surface. The input motions have been recorded on the surface. So we refer to these conditions as being outcrop conditions. Otherwise, let's say you had a sensor at depth. For example, the sites that I'm working on, like you see this D0, that's the sensor at depth, but we also have sensor, I mean, that's at the surface, but we also have sensors within the bedrock. So that's D6. So once you have a sensor at the bedrock, that's a different condition. That's not an outcropping motion because this is not at the surface. In this case, it has a within type motion, but that's really advanced for research purposes. For your project, you'll be always selecting outcrop for the type. And let's say I also want to look at the Fourier amplitude spectrum. So I will select Fourier amplitude spectrum. I would click OK. And you also have to specify the location and the type. You see, once I've added, like, let me remove this. You see, once you add a plot, you have the option to specify like the damping for the response spectrum, the minimum period at which you want to plot the results, the maximum periods, how many points between these two periods, and the spacing, whether log or linear. And you can also specify like the logging level, how much detail you'd like to see, medium, low, or high. So you see that's for the response spectrum. Once I add a Fourier response spectrum, Fourier amplitude spectrum, you will see another option for the Fourier amplitude spectrum. So I click OK. You see now I have options for the frequency properties, which you can modify if you'd like to. So it's always good to look at response and Fourier spectra, but really what you have to look at are the ratios. So that is the fourth tab over here. So this will provide you with three options, either the acceleration transfer function. It is always a good idea to look at the acceleration transfer function, and you should have talked about this in class. So I will add the acceleration transfer function. So simply the ratios over here, it's a ratio of two depths, something recorded at the surface divided by something recorded at depth. So that will give us the acceleration transfer function of the surface divided by that at bedrock. So if you click OK, you will get now two locations because now we're getting ratios. So it's always location 1 divided by location 2, meaning in this case, we have the surface at 0 meters divided by the bedrock at divided by the bedrock, which is at 46 meters in our this specific case. And again, you have to specify always the type. And again, for your project, it's always going to be outcrop, outcrop, outcrop. So I selected the acceleration transfer function. One other option, I can select the spectral ratio. So these are the amp factors, meaning the SA at the surface divided by the SA at bedrock. So it's always good to look at the amp factors. I'm going to click spectral ratio. Okay, again, it is the surface 0 meters divided by bedrock. So that's the default, and you will need to look at these for your project. Remember in the general settings, we had the option of varying the properties within the Monte Carlo framework, and that will show it like in this soil tabs. So don't worry about that. Simply, that is all the input you care about up to ratios. And again, you can specify how detailed you'd like your plots to be. The damping, the minimum period or frequency, the maximum period or frequency, how many points you want your results to be plotted at, and whether you want your results on log or linear scale. So now we've defined everything, soil type, soil profile, motions, and we specified what output we want to look at. So now we will do the computations. So let's go to compute. So once you're ready, you simply go over here and you click on this compute tab. So remember we had 7 motions and 1 shear velocity profile. So it's going to run each one of these individual motions through the soil profile, and you will get 7 different outputs for each motion. So for every output we specified in the previous tab, we will get for every motion we specified in the previous tab, we will get an output, and thus we will have 7 outputs for each motion. and we will look at those. So once I click compute, it's going to start the computations, the iterations. So I'm going to click compute. I have to save the file first. So make sure to save your file. I'm going to go demo. I already have that. Click save. Yes. So you see now the calculations are starting. It's telling me there are 7 trials. I have 1 site and 7 motions. So it will start with the first one, 1 out of 7, and it will tell you the name of the motion, and it will start that with the iterations. For example, in this case, the first iteration had a maximum error of 201.35. Remember, we specified a tolerance in the general settings tabs of 2%. So we told Strata to stop the iterations once it reaches an error of 2% or the iterations of 10. So in this case, the error in the first iteration was 200, and then 69, 13.4, 4.3, and then 1.87. Boom, that's below 2, it stopped. And so on for each of the motions. Let's say I specified the maximum number of iterations in the general setting as 5. Remember, you could specify either the error tolerance. Let me go back over here. You can either specify the error tolerance or the maximum number of iterations. So let's say I specified 5 over here. Any iteration that was, for example, in this case, it would have stopped at 5 with an error tolerance of 2.6, with an error of 2.62%. So the maximum number of iterations would have controlled in this case. So it's always good to check the errors here and make sure they are converging to values below 2%. Otherwise, go back and change the maximum number of iterations. So it computed was pretty quickly. It didn't take a lot of time. So now we can look at the results. So we go to the results tab. So you will get your results plotted, but also like if you select on plot, you will see a plot of the results, but also you can get the values in tables. And for your projects, it's always good to look at the plots within Strata, but it is recommended you copy the values from the data table and plot them nicely in your favorite plotting software. So do not present these plots in your report. Make nice plots, make good plots by simply copying the values from here, taking them to Excel, MATLAB, Python, whatever your favorite plotting software is, and plot the results nicely. But simply, it is always good to look at the results first, make sure the calculations are okay, and finally, once you're happy with the results, copy them from the tables and plot them. So here, remember we selected several options for the outputs. And you can look at different options by clicking on the output over here. These are all the output options we specified. We have our final VS profile, initial VS profile, etc. Let's look at the initial VS profile. Remember, we had 3 layers. The first layer with 300 meters per second, and then 250 meters per second, and then our bedrock with 950 meters per second. So that was our initial shear wave velocity profile. We can look at the final shear wave velocity profile. Remember, the VS value is going to change because G over G max is changing to be compatible with the induced strain. So that is the final shear wave velocity profile. And if you see, like the first layer got divided into sublayers because the strata is discretizing the layers. Remember, we selected this discretization option, layer discretization. So it's going to divide each layer to smaller sublayers such that we have a smoother transition and the strain. And that is the final, that is the shear wave velocity profile, but it's on log scale. So if you want to change anything in the plots, you can click over here, right click, plot options. You will always look at the VS generally in linear scale. So I'm gonna click linear, click OK. And you can also change like the scale options. You can uncheck automatic scale and like you can specify the limits of the axes. I'm gonna leave them as is. So remember, we had approximately 300 meters per second for the top layer. So with the induced strain, the actual G over G max will be less than 1. So your shear velocity will be less than the initial value. So that's why the shear velocity is less than 300, less than the initial value. And you can see we have a number of curves being plotted. We have gray curves. So each one of these gray curves corresponds to the result from a motion. We have 7 motions. So if I click on the motion, the results for this motion will be highlighted in green. So like you see the green color is going to change depending on which motion I select. We had 7 motions. And if you want to look at specific motion, let's say, oh, I want to know which motion is this one. I will go through them until it turns green. Let's see. So this one over here, that's motion 2. So if you want to look at a specific motion, that's how you do it. And then the blue lines, these are the median and the median plus minus one standard deviation. So if you could, for example, if you look at the data, at the table, you have the results for each motion. But if you scroll at the end, you have the median and you have the standard deviation. And these are the middle plot is the median and then median plus and minus one standard deviation. So that's for our shear wave velocity profile. And you have a legend over here. So that's like unselected motion, selected motion, that's the median, and then the median plus minus sigma plus minus standard deviation. So let's look at the peak ground acceleration versus depth. So that's our PGA versus depth. Again, we have 7 individual gray curves, and the one that is selected will be highlighted in green. Then we have the median and the median plus one standard deviation. Let's look at the peak strain. That's the maximum strain. So that's our maximum strain profile. And we're getting up to values of 0.1, probably like 0.5% over here. You can actually click and it will give you a value. For example, oh, that's 0.3, that's 0.4%. So if you want to look to know like what the specific value is, you simply left click on the plot and it will give you the coordinates. So that's 0.4% at 46 meters. We can also look at the ratios. Let's first look at like the acceleration response spectrum before looking at ratios. So these are the spectral accelerations for all of our motions, and these are at the surface. Remember, when we selected the output, we specified we want to see things at the surface. So these are the 7 motions, their spectral acceleration. We can look at Fourier amplitude spectra instead. So look, for example, this plot is not good. I can come over here, change the limits for the y-axis. Let's say it's, I know what the 0.1, 0.001. So now I have a better view of the plot. And again, I have 7 curves for each individual motion. So now let's look at the interesting stuff, the ratios. So let's look at the spectral acceleration, the transfer function. So you always have to change these. Let's go to 10. Okay. Let's go to 5. So that's my transfer function of the surface divided by the bedrock. So that's simply the Fourier amplitude spectrum of the surface divided by that at the bedrock. And you can see that's your fundamental mode, that's your second mode, etc. And if you want to know, the fundamental mode is at like a frequency of 1 Hertz, and it has a transfer function amplitude of approximately 3. And then we can look at spectral ratios, amp factors. So these are the amp factors. You have on the x-axis your period, and then the amp factor, which is the spectral acceleration at the surface divided by the spectral acceleration at bedrock. And again, you have an individual curve for each motion, and then you have the median and the median plus 1 standard deviation. So let's say you wanted to go back to your analyses, to your profile, and change something. You wanted to change the motions, you wanted to change the soil types. So once you have clicked compute, Strata will lock everything so that you won't be able to change it, so that you know what the results are to what input. So these results are for these inputs. So if I want to change something, it will not allow me. Like you come over here, it is locked. You cannot change it. You can't do anything with it. So it will lock your input values. And the only way to change is you go to tools and you click delete results. So that will delete your results. So let's say you wanted to change something with your results. Make sure to save them before you delete them to keep a version of the results you already computed. But if you want to change something in your input, you can do that without deleting the results that Strata already computed. So you go to tools and you click delete results, and that will unlock the inputs for you and allow you to change the inputs. So I'll click delete results, and now I can come over here, I can change the values. Previously, if the Strata computed results and the results are plotted, you cannot change the inputs. And now, like, because I click delete results, you don't have results anymore. You have to compute again. So let me just show you this damping limit. Let's say we specified a value of 5. And then we went to the results and click compute again. So it's going to do the same computations again over and over for each of our 7 motions. So again, all of them are converging pretty quickly. So just to point for your project, you'll probably be doing 21 analyses. I guess you have to do the base case hero velocity profile, and then the base case plus a certain percentage, so that's 2 VS profiles, and then the base case minus a certain percentage, that's 3. And then you have 7 motions, so 3 times 7, you will do 21 analyses, but you don't have to do 21 individual analyses. Again, you can see over here, we're running 7 analyses at once for the same hero velocity profile, so you can run 7 motions for the base case, 7 motions for the base case plus certain percentage, 7 motions for the base case minus a certain percentage, each one at once, all 7 motions together. Now let's look at the results. So I guess I didn't plot the damping. So let's go back and specify damping. And I'm gonna just select fewer motions just so that things, so you see now I have results, so I couldn't modify anything. I have to click delete results to be able to change. So I'm gonna uncheck these and only compute my results for fewer input motions. And I'm gonna select from the output specification, the damping. So the damping ratio versus depth. Then I'm gonna click compute again. So now I see I only have 3 motions because I disabled 4 of them. So let's look at the results. So let's look at the damping ratio particularly. Let's look in linear scale. And remember, I specified a damping limit of 5% over here. In the soil taps, I said damping limit of 5%. So you see it has everything at a minimum value of 5%, and that's really not ideal. So that's why be careful not to input a high value over here, because that will be the minimum damping. The Strata will enforce this as the minimum damping, no matter whether it is compatible with the strain or not. So be careful about this input. Make sure you have a very low value, probably 0, keep it as 0 so that you're not enforcing a damping, but rather the damping is being selected such that it is compatible with the induced strain. So I can't edit the results now because I can't edit the input now because I have results. So I have to click tool, delete results. And now I can go back and select 0 over here, and then I can compute again. And a damping profile will be compatible with the strain rather than the minimum value that I specified. So let's look at the results. You see now I have damping that actually matches the strain rather than the minimum value that was enforced by Strata, because that's the input that I selected. So be careful about that. So I guess that is pretty much everything I have to say. Again, you can look at the results in terms of plot, data tables, copy the values from the table. You can click, select all, right-click copy, and paste them to wherever you want to plot them nicely. And again, you'll have results for each motion, and then the last column will be the median and the standard deviation. So actually, I'm gonna give you my email address. If you have any questions, feel free to contact me. My email is mhallal@utexas.edu, and I'd be happy to help you and answer any questions, whether if you're having problems installing or downloading the software or using them, or any specific question about your project, I'd be happy to answer it. And that is everything. Thank you so much.